There is so much that has happened in the empirical world, and I guess through that fast-paced progress on the empirical side, a lot of us theorists were having some existential crisis, right? At least I was. What is the relevance? What should we be doing? What are the next set of problems we should be pursuing? Because up until that point, theory preceded practice. At least in machine learning, we'd come up with very concrete, principled approaches, and then we'd test them out, and it would work well. Right, so SVM started that way, for instance. But deep learning kind of turned that around, and the question is, what is the next generation set of algorithms we should be designing, analyzing, and thinking about, right? And that's what this talk, I hope to convince you that the optimization story is far from over. Although, most of what you see in practice today is SGD, and a lot of empiricists say it's SGD and that's all you need. But I hope I can convince you otherwise today. And that's the broad agenda in the talk. But in particular, I'll be focusing on the scenario of multi-agent optimization. So when we go beyond single agent and just one objective function, that's where I believe that we need more sophisticated algorithms. So doing just stochastic gradient descent, tuning hyperparameters, right, and seeing everything work wonderfully is no longer the case. And this is a work that will appear in Europe's. Florian Schäfer is a PhD student at Caltech. He comes from more applied math background and got interested in the problem of why GANs are so unstable and having all these issues of mode collapse and so on. So, and I think this kind of cross-fertilization is what we will see in this workshop. That's quite critical to think of new ways of approaching the old problems. And so the main idea is, if I want to think of single agent, it's very clear that there is one objective function. We want to get to hopefully the global minimum point, but we'd be happy even if it is a local minimum with some good properties. And that's where, as I said, stochastic gradient descent has been successful. But now, if we want to go to multi-agent and in particular competitive optimization, right? So the general multi-agent could be a large number of agents with their own objectives. But in this talk, I'll limit to 2 agents and briefly comment in the end. A lot of what we've developed extends in a natural way to more than 2, but let's keep it at 2. And even though I introduce here as 2 objectives, in most of the case, we'll just look at minimax problems, like problems in GANs and so on, where one is competing with the other. But most of, again, what I say today can also extend to the general case. And the idea is, right, so because each one is trying to optimize their own objective, it's no longer clear what is the right thing to do here. And in game theory, we have the notion of strategic equilibrium, thinking of it as a Nash equilibrium where each agent cannot get better on their own, right? And if we go to the non-convex case, then we can just make it into a local notion on lines of local optimal points. So this is one notion, we can agree on, saying that at least, if these are independent agents, they cannot on their own go to a better place. But it's not clear if this is what we really want in machine learning, because in most of the cases, we have the agents under control, right? We are designing the agents rather than the agents as having their own rationality and own beliefs and own objectives, right? This whole exercise is under our control. So we'll see later on, we can debate if this is even the right thing to do. But for now, let's start with the notion that we want to go to an equilibrium point and we want to converge. And in terms of applications for this, of course, I mentioned GANs. The experiments I'll show you will be all on GANs, but this area is so much bigger than just GANs, right? Because if you think of any form of robust optimization, then there is multiple set of parameters, and there's usually competition because you're looking at optimizing for the worst case, and in complex systems, you could have so many different constraints and objectives to optimize over. So that's a natural setup in machine learning to consider, and work that I won't talk today, but we are pursuing a lot at Caltech in collaboration with people in control systems and robotics is the use of robust machine learning. If you are building a deep learning system in the loop with a control feedback loop, right? We have to have safety, stability, and all these constraints. So we can't just put a black box network there with no guarantees. So what do we do in those cases? We can allude to a lot of results from robust optimization, robust statistics, and build upon that. So I won't talk about it today, but I think there's a lot of aspects we can pursue there. And of course, if you think of the very basic notion of constrained optimization through Lagrange multipliers, that's a minimax problem, right? So far, deep learning is mostly unconstrained. We hope that the data just drives the model to the right places. So if you augment the data and incorporate all the constraints to data augmentation, you hope that it will incorporate it. But in many cases, if you want strict constraints to be enforced, like in these safety critical systems, then you cannot just hope for that to happen. You have to enforce it. And once you incorporate Lagrange multipliers, it's no longer single agent, it's multi-agent optimization. And of course, once you go all the way up to like reinforcement learning in swarms of drones, and these are agents which have limited observability, limited communication, then it gets a lot more challenging. So to me, I believe that there'll be a lot more applications of multiple objectives, multiple agents we'll see in machine learning as we go along. And so now the question is, when it comes to optimization, what do we do here? Right? So the standard one that almost everybody except the optimization theorists use is the alternating gradient descent. Right? So in the case of these two agents, each agent just optimizes gradient on their own, and they hope for success. And it's argued that this is the natural extension of gradient descent to two agents, because now instead of one agent doing it, there are multiple ones. But unfortunately, this fails even in very simple cases. So perhaps the simplest case you can think of is bilinear game, right? So each, like the agent, it's just linear in each agent. And so what happens is, if you do alternating gradient descent, you can just keep oscillating. And this is an issue for all finite step sizes, right? So it's not even that you hope you tune a hyperparameter and then this goes away. It doesn't. And in fact, if you think about any kind of neural network architectures, the last layer is still linear. So in a way, when you're competing the generator with the discriminator, there is, right, like at least in the last layer, it's a bilinear game. So there's lots of oscillations, and we see that in practice. It's so gentle and brittle. I mean, you have to be so gentle that I have had interns and students who refuse to touch a working GAN, right? They don't want to change anything more if it works because it's so delicate. And so that's why I believe that alternating gradient descent is not a solution that would work for GANs. And so that's at least one source of all the issues in GANs. As I said, oscillation is one, but also we believe mode collapse. And I'll show you some experiments showing how even mode collapse can get better if you can fix the optimization. Because I don't claim optimization is all that is wrong in GANs, right? But we have to first fix that. And then we can hope for asking other questions and asking what the solutions are. And indeed, we are not the first ones to point out that there are oscillations and alternating gradient descent is not the right thing to do. There has been an extensive set of work, and of course, if you go all the way back to the classical game theory, right, so at least we attempted to go to the 50s. Maybe there's even others, of course, between 51 and 2017, there's a lot that has happened. But indeed, there is a lot in game theory, and there's a lot that has now come into the machine learning community through these works. And so what is the kind of new aspect? What is our viewpoint that differs or is not exactly the same as these works, right? So I believe the general notion is, right, like now instead of gradient descent, we have alternating gradient descent, but alternating gradient descent is unstable. Let's go ahead and fix that. Maybe we can add regularizations, we can add other terms, right, to fix that. We can think of like different notions of behavior that could help stabilize this. So at least in our view that instead of trying to fix alternating gradient descent, we wanted to ask, can we go back to thinking about what is the natural generalization of gradient descent to more agents? And what is the natural generalization of a local update rule to more agents? So what do I mean by that? Let me jump to the point directly. So if you think about gradient descent in one agent, right, what it's really doing is optimizing a local approximation, right? So it's taking the linear term, the Taylor series, so you have the second order penalty as a notion of the confidence level, right, of this approximation. So this is gradient descent. We are doing local approximation. So if you want to now think of this viewpoint and extend it to more agents, we can now ask what is the right way to think of local approximations for each player. So each player optimizes some form of its local approximation, right? We hope at least locally it goes to the Nash equilibrium of this local update, and then we can keep moving forward in this way. So of course, the first order extension of this, the first order version of this is just each player only looking at a linear approximation, right? So if it's linear in both the players, then you just get back alternating gradient descent. And we know that's unstable, so that's not enough for us. So what this is suggesting is maybe we should now look at the higher order approximation to get better properties. And so that's the viewpoint we take to extend it, where we say, okay, instead of jumping from linear to quadratic, for multiplayer games, we have the middle ground, right? So for these two agents, we can do bilinear, which still can be, right, like less expensive and has properties that's different from a full quadratic approximation. And so that's the view we take, that we'll now incorporate this mixed Hessian term. So it's bilinear, and each agent can now optimize this objective. And the idea is now it becomes interactive. So this is the lowest order approximation to have interactivity between the two agents. Because the linear one was just each agent optimizing their own gradients. But now we introduce this bilinear term. You incorporate this mixed Hessian, which can model what is the level of interactivity, right? So the idea is if this mixed Hessian has large singular values, there is strong interaction. If it's small, then there's weak interaction, right? So you can like look at what happens in these different regimes. And it turns out that in this case, in fact, you can compute this in closed form. You can think of that now, there is a preconditioner, right? So you have this inverse, and now you're also correcting for this mixed Hessian term. And so now, why bilinear and not general, quadratic, right, or second order optimization? So as I said, one is this is cheaper, so you're not looking at right, the full second order Hessian. The other is we believe that it's because it's rotationally invariant only on each agent and not overall, it still preserves, it breaks the symmetry between the rotational invariance of the overall set of variables on both the agents. So, and there could be many other reasons. But I think the idea is if we don't need to go to full quadratic, right, we have this middle ground, and that can, and also we have closed form solutions for that. So another way to think about what this competitive gradient descent is doing, right, so this is the update rule. So for both the agents, we can write them together, right? So we are kind of having this inverse term. I mean, this is part of the, right, like update here. I mean, this is the update here with the step size. And so now if I did the expansion, of course, assuming, right, that you choose the right step size so that you can write down the series. So, if you now look at each term, you look at increasing approximation with higher order term, what this is looking at is, right, like it's looking at trying to estimate what the other player is doing, right? So you're having this kind of like recursion of what you're thinking of the other player. Because if you just look at the first term, that's assuming that the other player is constant, right? The other player does nothing. If you look at the second term, it assumes that the other player thinks that you're constant. And the third term, recursively so on, right? So you could like kind of do different methods to approximate this inverse, and you get this like notion of what each agent thinks of the other player. So there is still this notion of awareness of different, varying degrees based on the kind of approximation you make for the inverse. So you don't have to do the exact inverse and do an expensive computation. And in fact, that's the idea. You can like kind of use more sophisticated Krylov subspace methods like conjugate gradient and come up with approximate solutions and still do much better than alternating gradient descent. So, and I think Lola was a algorithm that was proposed before that looked at opponent awareness, and you can think of competitive gradient descent as an infinite order opponent awareness, right? Because you're making sure that each player is aware of the other up to this bilinear approximation. And so I won't go into a lot of details with the other algorithms. Indeed, as I said, there are many others. And the main difference, I would say, is this now preconditioner term, right? So we have this term that is essentially accounting for large interaction. So if you don't have large interaction, that is a large singular values in the mixed Hessian, this doesn't matter, right? You can reduce it to some of the other algorithms. But when you have that, it still succeeds. And so the idea is you can now work with much larger step sizes and still get away with that. So that's the important aspect here. And so let me just, and we can also come up with exact results on for the convex concave case, saying that you can also work with large interaction. But I will skip that, and I want to like kind of point out a follow-up work that we have that shows how we can think of this competitive gradient descent as also for having some form of regularization in GANs, right? And it's implicit because the optimization algorithm itself incorporates some stabilization, and so you don't need a lot of other extra or explicit regularization to come up with good properties. And so let me walk through this. So let's now go back to just GANs and ask, why optimize this min-max problem, right? So typically there is a loss function where you maximize over the discriminator and minimize over the generator. And so the idea is, because I don't know what the distribution is, I don't know what moments I should use. So this is fully non-parametric, and that's why the GANs can be powerful for cases like natural images, because I don't know what to specify that I should optimize over, right? So, and that's the benefit of doing this. But the problem is this is so hard to optimize. And so people have come up with various ways to reason about GANs because we have all these complicated issues. So as I said, the first issue I've already covered, so I won't go much into it. One way to think is each agent is independent. The generator and discriminator on their own optimize their gradients. And so this form of independence can lead to good solution on their own. And we've shown that that is not true. So this viewpoint is mostly, right, like no one believes that anymore with respect to GANs. So I guess the second viewpoint is more nuanced, right? So the second one saying we hope we go to some kind of a global solution over the generator and discriminator, rather some Nash equilibrium, right? Of course, we can't go to global min and global max over independent on both the generator and discriminator. Since that is not possible, let's hope it goes to some Nash equilibrium. But the problem with this viewpoint is if you have finite data, you can always get a perfect discriminator, right? So the discriminator can be always perfect, and you kind of move your generator, the discriminator keeps, again, to 100% accuracy. And if you've trained GANs in practice, most of what's done is to limit this, right? So this is called overtraining of discriminator. And so all the regularization, everything is, can we limit the gradients of discriminator, limit what the discriminator can do? And so a lot of fixes is because, there is, if you hope for the Nash equilibrium, it doesn't exist in many of the cases. And you can just kind of end up getting this perfect discriminator when there is finite amount of data. And so the third viewpoint is, okay, let's not go to Nash globally, meaning it's an equilibrium point with respect to all global moves. Let's at least hope that it is a local Nash equilibrium, right? So you can at least hope for at least some local stability. And even here, right, it's not clear if those are the points we want to get to, because those that are good in terms of being local Nash may not end up leading to good generative models and vice versa. And again, there is a huge deviation with respect to what we can say in single agent versus multi-agent optimization, right? So with single agent optimization, we have all this correspondence between local and global optima, especially you over-parameterize the models to sufficient degrees, you can get a lot of nice guarantees. But there is no such analog for multi-agent, and that's why even this notion of local Nash can be hard, and can be hard to reach as well in many cases. So the viewpoint of this competitive gradient descent, I believe, is saying is let's constrain the game itself in terms of what each player knows about the other player, right? Because we are doing local approximations of the objective, so each player is not seeing the full global view of the objective. And also each player is assuming what the other player is doing in terms of how much observability they have and what kind of strategies they are doing. So instead of just specifying the min-max objective, if we can also model broadly, right, all these other aspects of the game. How should I think about limiting information among the players? What kind of moves do I allow? How large can those moves be? If you're doing some form of gradient descent and limited step size, you're already limiting the moves. So I think this notion of limiting information and limiting what the awareness is of the other player can be some critical ways to stabilize the game implicitly. And that's why we call it implicit competitive regularization, because instead of adding explicit regularization to the objectives, we are instead saying what each player can do and what it knows, right, and what it knows about the other player. So let me show one simple way to think about this. This is a toy example. And here you see that there are these kind of exponentials, but you have this bilinear term, right? And the idea is if you make this alpha large enough, you can always run off to infinity. So each player can just kind of run off and not go to an equilibrium, right? So given this, this is a Nashless game, but can we hope for some stabilization here? Right, so because if we limit what the players can do, they can still go to a convergence point. And that's the idea that, first of all, we'll limit the step size. They can only do local moves. But if we don't limit the knowledge of the loss function, right, they will just run off to infinity. And this is the analog of the discriminator getting overtrained and always just overtaking the generator. Right, so you don't want this to happen. So you don't want to give the complete view of the objective function. You want to limit this. On the other hand, if you do local approximation and do alternating gradient descent, for instance, right, you're ignoring the other player, and that's also bad. That leads to oscillations. And so what you can think of the competitive gradient descent as doing is the mix of these two, right? You're limiting to only local approximation. So you can't overtrain the discriminator to overwhelm the generator. But also there is awareness of the other player, right? So unlike alternating gradient descent, you are now incorporating the interactivity between the generator and discriminator. And that's why, in this toy example, you get to convergence, it's near zero, which is okay, even if it's not exactly zero. So you can get to some stabilization because of this implicit regularization. And so that's the main kind of principle here, that we are using the interactivity to reduce the gradient of the other player, right? So what gradient penalties were doing to limit the discriminator, we can do this now more implicitly by thinking of this as competitive gradient descent. And that's the main message I wanted to give here. And we have results in the paper. You can take a look there. The main idea is, we took the standard Wasserstein GAN architectures, the hyperparameters that were already there, right? We didn't even tune any hyperparameters, and we got to better inception score. And we did the adaptive version of competitive gradient descent. That's the only thing we added. But there was no extra regularization. So the idea is there's no explicit gradient penalty needed, and so less hyperparameters to tune for and more stability. And we also show in the paper that mode collapse as well, we can show that there is better performance. And so the idea is we can come up with principles, theory, and also see the gains in experiments, right? And we hope to scale this up. So I didn't talk about the computation, but we have the PyTorch code available. This just requires Hessian vector products. So if you have both forward and backward mode differentiation, this is just like twice the expenditure, right? But I hope the JAX is the new framework. I hope it gets more support and integration with the deep learning frameworks. Then you can speed up all the way. But even with what we have today, we've been able to run them without too much overhead compared to the baselines. So how much time do I have? Oh, it's there. Few minutes. So to summarize, the idea is when we go from single agent to multi-agent optimization, the story gets much more muddled, right? Because there isn't this notion of one or set of global optimal points to go to. Each agent has their own objective. You may not even have a Nash equilibrium. You may just keep oscillating. What do you do in that case, right? And that's where I think there is a lot more room to come up with sophisticated algorithmic design. And what we attempted to do is go back to the notion of what each player knows, what each player knows about the other player, what kind of approximations each player does, and hope that, that by going to a Nash equilibrium of these local updates, you can also overall stabilize this game. And indeed, there's been a history of work in stabilizing GANs and stabilizing this multi-agent optimization. And what I see our work as kind of, right, in many special cases, they reduce to these previous algorithms. So the main, I would say, advance is when we have strong interaction, we don't have to limit the step size to the same extent as the other algorithms. So we can train with much larger step sizes, so we can be a lot faster, and especially if we are having these kind of preconditioning step with the inverses, in many cases you can have these conjugate gradient and other approximations and still be efficient. So you can get computational efficiency, you can get stability, and we saw that it also provides this implicit regularization that's actually needed in many cases, such as GANs, because by themselves they may not even have a Nash equilibrium. And indeed, there is so much more to do beyond, right? Like this multi-agents, what is the right notion? Of course, you can think of a multilinear approximation instead of the full higher order approximation of these multiple agents. And like some of the work I've done with tensors has been looking at low-rank tensor forms, right? So you could look at like kind of structured ways to come up with efficient algorithms for multiple players. But in machine learning, we have not even been thinking in terms of what to do with more than two, right? Because two has been hard enough. But maybe now you can think of, what would it mean to have many agents? Maybe you can like kind of say one set of objectives can kind of be responsible, one agent can be responsible, and another can be for another set of objectives. Because if we go into any kind of practical system, especially that gets deployed in social media or in the world with humans as interacting agents, this is so critical to think of it as mechanism design and as what are the abilities and information that each agent has, right? So I hope that we can go beyond like the simple two-agent GAN game to these much bigger and very important problems on how AI interacts with humans and other agents in the world. Thank you.